Welcome back to gas pneumatic propulsion video lecture. So it is the last unit 5, space propulsion. I am Dr. Ananda Kumar, Assistant Professor, Department of Mechanical Engineering, GZ Tirunelveli. So the introduction of the space propulsion, rocket propulsion or space propulsion. In the section about the rocket equation, we explored some of the issues surrounding the performance of the whole rocket. What we did not explore was the heat of the rocket motor. In this section, we will look at the design of motor and the factors which affect the performance of the motor and some of the practical limitation of the motor design. The first part of this section is necessarily descriptive as the chemistry, the thermodynamics and the maths associated with motor design are beyond the target audience of this website. General principle of the rocket motor. In a rocket motor, a chemical reaction is used to generate the hot gas in a confined space called the combustion chamber. The chamber has a single exit through a constriction called the throat. The pressure of the hot gas is higher than the surrounding atmosphere. Thus, the gas flows out through the constriction and is accelerated. Propellant. The chemical reaction in model rocket motor is referred to as an exothermal redox reaction. The term exothermal means that the reaction gives off heat, and in the case of rocket motor, this heat is mainly absorbed by the propellant, raising their temperature. The term redox means that it is an oxidation and reduction reaction. In other words, one of the chemical transfer oxygen atoms to another during the reaction. The two chemicals are called the oxidizing agent and the reducing agent. The most popular rocket motor are black powder motor, where the oxidizing agent is saltpeter and the reducing agents are sulfur and the carbon. Other motor include potassium or ammonium perchlorate as the oxidizing agent and a mixture of hydrocarbon and fine powdered metals as the reducing agent. Other chemicals are often added, such as retardant to slow down the rate of the burn, binding agents to hold the fuel target together, or chemical to color the flame or smoke for effect. In hybrid motor, a gaseous oxidizer, nitrous oxide, react with the hydrocarbon such as plastic to produce the hot gas. Energy conversion. This reaction releases energy in the form of the heat, and by confining the gas within the combustion chamber, we give it energy due to its pressure. We refer to the energy of this hot pressurized gas as enthalpy. By releasing the gas through the throat, the rocket motor taps the enthalpy of the gas into the flow of the gas with the kinetic energy. It is this release of energy which powers the rocket. So the energy undergoes to conversion. Chemical energy to enthalpy to kinetic energy. The conversion from chemical energy to enthalpy takes place in the combustion chamber. To obtain the maximum enthalpy, it is clearly important to have a reaction which releases of heat and generate a lot of high energy molecules of gas to maximize pressure. It is clearly a limit to the temperature and the pressure as the combustion chamber may melt or split if these two are high. The designer has a limitation placed on his choice of the reagent, in that the reaction must not heat the combustion chamber to a point where it is damaged, nor must the pressure exceed that which the chamber can survive. Changing enthalpy to kinetic energy takes place in the throat and the nozzle. Our mass of the hot flue gas flow into the throat, accelerating as the throat converges. If you reduce the chamber of the throat enough, the flow will accelerate to the speed of sound. at which point something unexpected occurs. As the flow drives into the nozzle, it continues to accelerate beyond the speed of the sound. In the increase in velocity depending on the increase in area. This type of nozzle is called D-level nozzle. Kinetic energy of your body. If you consider small volume of gas, it will have very low mass. As we accelerate this gas, it gains kinetic energy proportional to the square of the velocity. So if you double the velocity, we get 4 times the kinetic energy. The velocity of the supersonic flow increases the proportional to the increase in area of the nozzle. Thus, the kinetic energy increases by the fourth power of the increase in nozzle diameter. Thus, doubling the nozzle diameter increasing the kinetic energy by 16 times. The D-level nozzle makes the rocket motor possible as only such high velocity flow can generate the energy required to accelerate the rocket. In model rocket, the reaction is chemical, generally short-lived, a few seconds at most. So the amount of heat transfer to the structural part of the motor is limited. Also, in the liner of the motor casing to the casing acts to insulate the casing from the rapid rise in temperature, which would result from a reaction in direct contact with the metal casing. Model rocket motor also run at quite low pressure, well below the limit if the motor casing further protecting the casing. It can be seen that the enthalpy of model rocket motor is thus quite low. In large vehicles such as Ariane, the pressure and temperature are high, and the band may last several minutes, and the mass budget for the designer is very tight. Designing motor for this purpose is highly complex. Thrust. The basic principle of a rocket motor relatively straightforward to understand. In rocket, the motor exists to accelerate the rocket, thus it has to develop force called a thrust. One of several definitions of force is that force equal to rate of change of momentum. If we ignore any external effect, we can say that the thrust is entirely to the momentum of the propeller, a force called the momentum thrust. If you denote the thrust as F and the momentum as P, then automatically thrust equal to change in pressure to change with respect to time. Sometimes for mathematical clarity we use the notation P with a dot on the top to denote the first derivative of P and with the two dots for the second derivative. Thus in this new notation F equal to P dot. You may also recall from the section on the rocket equation that momentum is the product of the mass and velocity. Momentum P equal to mv. Therefore, F equal to mv divided by change in other different dt dv divided by d of mv divided by d of t. The exhaust velocity remains constant, which is a reasonable assumption. We arrive at the equation F equal to m dot ve. The term m dot is known as the mass flow rate. In other words, the rate at which mass is ejected through the nozzle in kg per second. In other words, this is rate at which the rocket band fuel. This is interesting relationship which can be expressed in bands. Momentum thrust. Thrust equal to mass flow rate into exhaust velocity. Flow expansion. The propellant is accelerated into atmosphere. As it leaves the nozzle, the propellant has an exit pressure and enters an atmospheric, which is a pressure P atmosphere. The transition from one pressure to the other cannot happen instantaneously, as any pressure difference will cause a flow of high pressure fluid into the low pressure region. So the force depends on the pressure difference and the area. So F equal to mVA plus A into P exit minus P atmosphere. Types of rocket engine. Rocket or rocket vehicle is a missile, spacecraft, aircraft or other vehicle which obtain thrust from a rocket engine. In all rocket, the exhaust is formed entirely from propellant carried with the rocket before use. Rocket engine work by action and reaction. Rocket engine push rocket forward simply by throwing their exhaust backward extremely fast. Rockets for military and recreational uses data date back to the 13th century. Significant scientific, interplanetary and industrial use did not occur until 20th century, when rocket was the enabling technology of the space age, including setting foot on the moon. Rockets are used for fireworks, weaponry, ejection seats, launch vehicle for artificial satellites, human spaceflight, and exploration of the other planet. While comparatively inefficient for low-speed use, they are very lightweight and powerful, capable of generating a large accelerating and of attaining extremely high speed with reasonable efficiency. Chemical rockets are the most common type of rocket, and they typically create their exhaust by the combustion of rocket propellant. Chemical rockets store a large amount of energy in an easily released form and can be very dangerous. However, careful design, testing, construction, and use minimize risk. Rocket vehicles are often constructed in the archetypal tall, thin rocket ship that takes off vertically. But there are actually many different types of the rocket, including tiny model such as balloon, water rocket, skull rocket, or small solid rocket that can be purchased at a hobby store. Missile space rocket such as the enormous Saturn V used for the Apollo program. Rocket cars, rocket bike, rocket powered aircrafts. Okay, including rocket assisted takeoff conventional aircrafts, rocket slugs rocket train, rocket torpedoes, rocket powered jet packs, rapid escape system such as ejection seats and launch escape system, space propellant. Propellant is a material that is used to move an object. Propel. The material is usually expelled by gas pressure through a nozzle. The pressure may be from a compressed gas or a gas produced by a chemical reaction. In the exhaust material may be gas, liquid, plasma before the chemical reaction in the solid, liquid killed. Common chemical propellant gas. Common chemical propellant consists of the fuel like gasoline, jet fuel, rocket fuel, and oxidizer. Propellant used for propulsion technically. The word propellant is the general name for chemical used to create thrust. For vehicle, the term propellant refer only to chemicals that are stored within the vehicle period to use and exclude atmospheric gas or other material that may be collected in the operation. Almost the English-speaking layman used to having fuel propel vehicle, or yet the word fuel is inappropriately used. In Germany the word temporarily derived stuff is used. In France, the word ecology is used. It has the same Greek roots as hypercloic, a term used in English for propellant which is combined spontaneously and do not have to set LBC by auxiliary ignition system. In rocket, the most common combination are high propellant, which use two chemical, a fuel and oxidizer. There is a possibility of tripropellant combination, which takes advantages the ability of the substances with smaller atoms to attain great exhaust velocity and hence propulsion efficiency at a given temperature. Although not used in practice, the most developed tripropellant system involves adding a third propellant tank containing a liquid hydrogen to do this. Thank you. The next topic is solid propellant in next video.